Hello again, physics friends. We are going to do some practice problems as a refresher before we get going for this term. Now, these problems are not going to be an exhaustive coverage of mechanics at the Physics 107 level, but they are just meant to get the gears turning again. It may have been some time since you've worked on problems like these. So we're going to start with this problem. We have a projectile that's fired horizontally. It goes through this tube and then emerges on the other side of the tube and then is in free fall towards the ground. The trick, though, is that there's friction in the tube. So that means although moving through the tube gets the ball further horizontally, it also slows the ball down. We're told that the acceleration in the tube, the deceleration, is negative a. A is a positive quantity, so that means we have a leftward acceleration on the ball as the ball moves to the right. And then once the projectile leaves the tube, the only force acting on it is gravity, so we expect a parabolic trajectory down to the ground. And we're asked two different questions. What is this total horizontal distance that the projectile travels as a function of the given parameters? The length of the tube, the height of the tube, the initial velocity v0 before entering the tube, the acceleration due to gravity, and the acceleration in the tube. And then in part B, what tube length gives you the maximum horizontal travel distance, L? And there you can see there's a trade-off. You could make the tube really long, and the ball would travel very far, except if you make the tube too long, the ball will come to rest in the tube, and it will never get to the end of the tube. And also, the ball does still travel horizontally after exiting the tube, so you don't want the velocity of the ball to be too small at exit of the tube. So this is an interesting optimization problem. Well, why don't we start with part A? And before we actually start solving the problem, let's just characterize the problem, right? So here we have, it's almost like two separate problems, okay? First, there's 1D motion in the tube, and there's a constant acceleration. And then after leaving the tube, now we have 2D motion in the air, in free fall, and that's also a constant acceleration in the y direction, and then zero acceleration in the x direction, right? There's no left-right force once the ball has left the tube. Let's also annotate this diagram a little bit to say when the projectile gets to the end of the tube, let's call its velocity there v. Okay, so it starts with an initial velocity v0, it slows down as it goes through the tube, and it emerges with a new velocity v. So we have a couple of things that we can do here. We can think of this distance L that we're trying to find as being made up of two pieces. One is the length of the tube, and the other is v times t, where v is the exit velocity from the tube, and t here is the time it takes for the ball to fall once the ball has left the tube. Okay. So the first thing I want to do then is find this velocity v, given that we know how far the ball travels in the tube, its initial velocity, and this constant acceleration. So let's work on that part. That's problem 1, or my subpart 1 that I identified here. And you likely recall that for constant acceleration, 1D motion, we can relate the initial and final velocities, the acceleration and the distance traveled in this way. Vf squared equals v initial squared plus 2at. And here we know that v0 we're just given as v0. We're told that the acceleration is minus a, and we're told that the distance traveled through the tube is x. And we are calling in this problem the final velocity v. That's the velocity at the exit of the tube. So we have an expression for v then. We can say that v is equal to the square root of v0 squared minus 2ax. Okay, so that is our exit speed at the end of the tube. So then in part 2, the quantity that we really need to know is how long is the ball in the air after it leaves the tube? In other words, what is the fall time? Okay, and the fall time we can get because we know the ball has no vertical velocity, no vertical component to its velocity when it exits the tube. So the time it takes for the ball to fall to the ground is the same as it would be if you just released the ball from rest, because the y velocity in both cases is 0. So here we're trying to find the fall time. Okay, and for that we can use the following. Okay, we have this 1D kinematics equation for motion in the y direction. The final height is equal to the initial height plus the initial velocity in the y direction, t, plus 1/2 at squared. In this problem, there is no initial velocity in the y direction, and also in this problem, the acceleration here is downward, and it's the acceleration due to gravity. The final y position is 0, and the ball starts at a height h. So what are we assuming here? I should have drawn this earlier, but I'll define a coordinate system where y increases as we go up, and we're calling the ground a height y0, and so the initial height of the ball is a height h, and that's true even when the ball is exiting from the tube. Okay, so we can then come back to this equation and start solving. We find 0 equals h minus 1/2 gt squared, or in other words, t is equal to the square root of 2h over g. That's how long it takes for the ball to fall, whether it's shot horizontally or released from rest. And so now we know something about the distance that the ball is going to travel. We know that that distance, total distance L, this is the total horizontal distance, that was given by x plus vt. And now we have actually an expression for v and t. V is square root of v naught squared minus 2ax, and t is square root 2h over g. Okay, so we'll just leave that right here in a purple box. That's our solution to part A. We have the distance traveled in terms of the given quantities, a, x, g, h, and v naught. Okay, in part B, we're asked what value of tube length gives us the maximum total travel distance. So in other words, we want to choose x, the tube length, to maximize L, given that we know how to write L in terms of x. So this just screams for a derivative. But again, before we dive in to doing any math, let's just make sure that our right-hand side is kind of sensible. Well, number one, it benefits you to have a longer x. In other words, L grows as x grows because the tube carries you horizontally. So the longer the tube is, the further to the right you'll go. The exception, though, is that the acceleration in the tube, which is slowing down the projectile, is a competing effect. It means you want a shorter tube. Otherwise, if your tube is too long, the ball will stop in the tube and it will never have a chance to even fall down. Okay, so that's why we have x appearing with a minus sign here. So there are two terms. The first term grows with x, the second term shrinks with x. So that suggests that there's probably an optimal value of x that will give you the longest value of L. Now we can turn to calculus here to help us. We know that to maximize L, we're looking for a position, or a choice of x rather, such that the derivative of that length L with respect to x is 0. That tells you we're at an extremum. And so we can take the derivative. On the right-hand side, the derivative of x with respect to itself is 1. And then we get to do some chain rule here. We have this root 2gh, that's a constant. Sorry, root 2h over g, that's a constant. We leave that alone. And then we have to take the derivative of this square root term. So we're going to get a 1/2 from that. 1/2 times v naught squared minus 2ax to the minus 3/2, to the minus 1/2 power, 1/2 power minus 1 is negative 1/2 power, times the derivative of what's inside with respect to x. Well, this is a constant, so that goes away, and then we're just left with a minus 2a, like so. All right, we have some cancellations. 2 cancels. This minus sign swaps to that to give a plus overall, and we can now write this out in the following way. We can have, we also have this term here is a 1 over a square root, And so we can separate the terms on either side, and we'll have something that looks like this. Square root 2h over g on one side times a is equal to square root of v naught squared minus 2ax. Okay. And then all that's left now is really the math crank. Turn the math crank. We can square both sides and then solve for x. Okay. So when we square both sides, we will get an a squared 2h over g equals v naught squared minus 2ax. And you continue to rearrange 2ax v naught squared minus a squared 2h over g, and then solve for x. Like so. Okay, first of all, we've done a lot of algebra. Let's make sure that we haven't made some silly mistake. So let's look at some units, right? Is this a quantity that has units of length? Square of velocity over acceleration, indeed, that's meters squared per second squared divided by meters per second squared. We're left with meters, check. How about this one? Meters squared per second squared in the numerator divided by meters per second squared in the denominator. Again, we have meters, check, so that's good. How about the magnitude of this quantity x? Well, I see that it's a number that's smaller than v naught squared over 2a because I'm subtracting off this quantity here. Does that make sense? Well, yes, absolutely, that makes sense. If we look back to our answer to the first part, if my length x were equal to v naught squared over 2a, then this square root term would be 0. And that's equivalent to saying that the ball basically comes to rest right at the end of the tube and then it falls straight down, so that the total distance traveled is just x. Okay. Good. So I want an acceleration that's going to be, I want a length of tube that's going to be smaller than it would be if the ball just fell straight down. So I want the ball to have some velocity when it comes out of the tube. I don't want it to just plop straight down. So that's why we have this minus HA over G present. There is an important caveat, though. It is possible in that solution for x to be negative, which would be a non-physical outcome, right? The ball's never going to go to the like, you can't have a negative tube length, basically is what we're saying. So that happens. So x is 0 when the two terms on the right-hand side are equal to each other. V naught squared over 2a is equal to HA over G. Okay, so that corresponds to an acceleration in the tube that is equal to V naught times the square root of G over 2H. You can rearrange and show that that's true. Okay, so our solution here is valid if A is less than that acceleration. In other words, if the ball doesn't slow down too much in the tube. Okay, but if the acceleration is bigger than V naught root G over 2H, then we have a little problem, and we have to think more about that one. And let's think about what this is saying. We're saying if the ball slows down with a very large negative acceleration in the tube, that means the tube is having such a big impact on the motion of the ball that we're better off without the tube. And indeed, you are much better off having no tube at all. So if the acceleration in the tube is too big, the ball slows down too much, you're better off having no tube. Then you just shoot the ball straight out, and the ball will travel as far as it goes according to 2D projectile motion under the influence of gravity alone. Okay, the other thing I think it's worthwhile doing is you have an answer. It's always helpful to look at limiting cases. Okay, so let's look at some limiting cases, or specifically one limiting case. What if the acceleration is 0? In other words, you have a tube and the ball doesn't slow down at all in the tube. How long of a tube should you make? Well, in the limit of no acceleration, no slowing down in the tube, this second term goes to 0. There's no penalty for having a tube. And in fact, notice as A goes to 0 in the tube, this right-hand side, the first term goes to infinity. meaning that x goes to infinity. So this is saying when you have smaller and smaller friction in the tube, you want a larger and larger tube. Does that make sense? Well, yeah, I think that does make sense, because if you have very little friction in the tube, then you're better off having an infinitely long tube. The ball will travel just as far as the tube, and there's no penalty to being in the tube. So the longer the tube, the better you are. Okay. All right, and there are other limiting tests you can do, but I think that for now, we've kind of got our point across. So we will wrap this problem for now, and we'll do one more. Okay, so our next problem will focus on the following, which I really like because it shows really clearly that a problem that seems really challenging can be broken down into smaller steps, each one of which is a little bit less daunting. Okay, so here we have a string attached to a ceiling with a bob at the end or a mass at the end, and everything is configured so that the mass is moving in a horizontal circle. And we know the string length, the angle that the string makes with the vertical, and the mass of the object. And we're told that at some point the string is cut, the mass is shot off, and we want to know how far the string travels, what horizontal distance specifically does the mass cover between the time its string is cut and the time the mass hits the floor. So again, before we dive into any equations, let's just kind of talk about some intuition here. Right, we know that the velocity vector at any given instant is always tangent to the trajectory, and this trajectory is a circle, right? So if we were looking at this from above, we would have something like circular motion. So this is a view from above, and we have the mass moving around this circle, so we can represent that with the blue ball, and we can give a velocity vector to the mass. Now, the speed is going to be constant, but the velocity is not, because the direction of the velocity is changing with time. When the string is cut, then the mass is just going to be shot off in a straight line pointing along the velocity vector at the instant that the string was cut. So we can think about breaking this problem down into two steps. One is, what is the speed of the ball, or speed of the mass, given that it's moving in a circle? And for that, we're going to use force diagrams and Newton's laws. Then, once we know the speed, how far horizontally does ball travel given an initial horizontal speed v that we're going to find in part 1. Okay, so let's dive into it then. Okay, so here we go. I've just copied this scenario graphically over here, and I'm going to start drawing a force diagram for this ball. I'll color it to match the color here. So on the right-hand side, I'm going to turn this into a force diagram. So I think, okay, long-range forces and contact forces, object of interest, I'll circle. Any contact force must necessarily cross through that red circle. So I have a string that's in contact with my ball, so I know there's going to be an associated force. I'll call that the tension force. Okay, and then there's no other contact forces because nothing else is penetrating that red circle, but there is a long-range force, and we know there's going to be a long-range force of gravity that's going to point down. So I'll write that down, Fg, and I know something about the magnitude of Fg. It's equal to the mass of the object times little g. Okay. Now, I got to ask myself, is there acceleration in the y direction? And the answer is no. The ball is not moving up, it's not moving down, it's not accelerating in the y direction. There's no change of its vertical velocity. Vertical velocity is always 0. How about in the x direction? Is there an acceleration? Is the velocity in the x direction changing? Absolutely. The speed is not changing, but the velocity most certainly is, because the velocity vector is changing its direction. So there has to be an acceleration in the horizontal direction in order for that to happen. And that is going to be an acceleration of a known amount. It's going to be v squared over r, because we know that we have uniform circular motion. And so the net acceleration is going to be radially inward, and it's going to have magnitude v squared over r. Well, what is r? R is the radius of that circle, okay? So if we're going to draw this, r is the radius of the circle, which is not the length L of the string, but it's L times the sine of theta, okay? So we can additionally write down that r for the circle is L times the sine of theta. All right, so we now care about the acceleration in the horizontal direction. So let's look at our system here, and let's map out our coordinate system. So we gotta have a coordinate system. I'm gonna call y increasing upwards and x increasing to the left. And what forces do I have that are left and right? Well, I only have one, right? The only force I have that's left and right is the tension force. So I could write the x component of the tension force and the y component of the tension force. There's no x component of the gravitational force. Okay, so here I go. I'm going to look at forces in the x direction. Okay, I know that the acceleration in the x direction is equal to 1 over m times the net force in the x direction. And I also know by this equation that my acceleration in the x direction has a very specific value. It's v squared over L sine theta. My net force in the x direction is the x component of the tension. So from this, I can say, okay, my v squared is equal to L sine theta times the tension divided by the mass m. I don't know what the tension is, though, so I need to do a little more work here to figure out what this tension is going to be. And for that, I can look back at my force diagram, and I know that mg down is balanced by my upward tension tx up. So I can say the same thing by Newton's second law. The y acceleration is equal to 1 over m times the net force in the y direction. And I have no acceleration in the y direction. And so my net force will be the y tension minus mg. And from that, I know that ty is equal to mg. Well, I also know something about how tx and ty are related through this angle theta. Right? I know that my tangent of that angle theta is equal to the x component over the y component. So my tx is equal to ty times the tangent of theta. Ty, though, I just found was equal to mg. Okay. So I can say tx is equal to mg tangent of theta. Okay. So now I'm in good shape, because in order to find the speed, I need to know tx, and now I have an expression for tx. So I'm going to combine my equations here by replacing that tx with my expression for tx in terms of mg and theta. So here I'm merging these two equations. To give the following: v squared is equal to L sine theta over m times mg tangent of theta. The m's cancel, and I can square root both sides to find that my speed is given by Lg sine theta tan theta. So now that we've kind of solved part one here, what is the speed of the ball as it moves in a circle, we can move on to part two. How far horizontally does that ball travel given an initial horizontal speed? So for that, we can kind of turn to a diagram that looks something like this. We can think about a ground, and having a ball some height off the ground shot horizontally with now a known speed given by v, and that ball is some height off the ground. We're not given h, but we can figure it out from the diagram. See, we know that the pivot point is a height L off the ground, and if we know the length of the string and this angle theta, then we can figure out these two heights. We can subtract the smaller from the bigger, and that'll tell us how far off the ground we are, and we can write that out very clearly here. We could say the height h is given by L minus L cosine of theta, like so. Or if you'd like, you can factor out the L and write the height as L times 1 minus cosine theta. Okay, so this is just a projectile motion problem. In fact, there's overlap with the previous problem that we did. Right, we need to know how far this ball is going to travel. We know the horizontal distance that this ball will travel is given by, so let's call x the distance traveled horizontally. And we know that that distance is going to be v times t, where t is the time it takes to fall. Okay. Again, we can use 1D kinematics information to find the time it takes to fall. We know the final height is equal to the initial height plus the initial y velocity, or v initial y, times t plus 1/2 at squared. Well, we know there's no initial y velocity, right? We're starting at a height h and we're ending on the ground. And what is our acceleration? Well, it's minus g. Again, I'm implicitly assuming here a y-coordinate system that increases as you go up, and we'll call 0 the ground, and h is the initial start. So we can flesh this out. 0 equals h minus 1/2 gt squared. So how long does it take? Well, it takes a time given by 2h over g square rooted. So we can bring this back over to our horizontal distance. It's v times the time it takes to fall, which is the square root of 2 times the initial height, which we know is L times 1 minus cosine theta, divided by little g. So now we're very close. We just need to stitch things together. Here we have a v, and in part 1 we solved for that v. So we can combine all of these things in the following way. We'll replace that v with this one, and we'll say the total distance traveled in the horizontal direction is simply square root LG sine tangent, also times square root of 2L 1 minus cosine theta over g, and we get a little bit of cancellation, but not too much. 1 factor of g cancels 1 factor of g. We get 2 factors of L both under a square root, so that L will pop out, and we end up with L times the square root of 2 sine theta tan theta 1 minus cos theta. So I don't know if you think this is pretty or not pretty, but there are a lot of terms on the right-hand side, and I think it's worthwhile not just boxing it up and running away and closing our eyes and pretending everything's fine without checking. We should definitely check that this is a sensible result. Okay, so let's take some limits, okay? So let's look at some limiting cases here. Okay, well, in our first case, let's look at the limit where the angle goes to 0. In other words, the bob is hanging straight down. Well, if the bob is hanging straight down, it's basically touching the ground to begin with. And also, what velocity will the bob have in order for the bob to hang straight down? No, there's no velocity. So when you cut the string, it's not going to go anywhere horizontally. So we hope that we would find x equals 0 when theta equals 0. And indeed, if you put in theta equals 0, sine of theta is 0, and so is 1 minus cosine. And so is tangent. So yes, we have 0 on the right-hand side. So case 1, when theta goes to 0, we find x equals 0, and that matches our expectation. So that's good. What about if theta goes to 90? Well, as the angle theta goes to 90, then that's basically saying we have a horizontal circle all the way up parallel with the ceiling. Well, in order for that to happen, the velocity of the ball has to approach infinity. So we would expect that the horizontal distance traveled when you cut the rope would also approach infinity. And is that indeed the case? Yes, it is, because when theta goes to 90, sine of theta becomes 1, cosine goes to 0, and we have the square root of tangent of 90 degrees, which is essentially approaching infinity. So that tells us that horizontal distance traveled will be very large, approaching infinity as theta approaches 90. You might be surprised to see, so those are all good things, and you might be surprised to see that the answer for the horizontal distance traveled does not depend on g. Well, that's maybe a surprise. But I guess maybe it's not so bad because, or maybe understandable, because if g is large, you have to have the ball travel faster and faster to reach a given angle. And so that it's true the ball will fall to the ground faster for a given height if g is larger, but also the initial horizontal velocity would have to be larger in order to maintain a circle at that height. And so those two effects exactly cancel out, and you're left with a distance that depends only on theta and L, but not on g. Kind of nice. Okay, I think with that we're going to wrap up. We did a couple practice problems involving kinematics in both cases and force diagrams and Newton's laws and circular motion in the other case. As I said at the start, the goal here is not to do examples that cover all of mechanics at the level of Physics 107, but just to kind of refresh our memory about what intro mechanics topics look like and how to do practice problems, just as a foundation for what's coming next. All right, until next time, take care and be well.